So, good morning, everyone. My name is Julian. I'm an evangelist with AWS, and I focus on AI and machine learning. And today I have multiple sessions, and you just listened to Adrian giving you an overview on machine learning on AWS, different layers, etc. And in this session, we're going to look at a specific domain called deep learning, and we're going to try and understand what the underlying theory, what the underlying concepts are when it comes to deep learning. And later today, we will use those concepts and to actually write and run deep learning code, train models, predict with those models using MXNet, and probably Keras, time permitting. And at the end of the day, we'll have a session on SageMaker, which is a new service that lets you train and predict at scale on AWS. Okay, but for now, let's focus on deep learning and try to understand why it works the way it works. So, of course, we'll look at some of the concepts, some of the theory. There's just a little bit of math, but not too much, I promise. One of my goals is really to try and explain this to everybody, even if you don't have a math PhD, right? Which is not my case either, so that's fine. Then we look at some network architectures, convolutional neural networks, LSTMs, etc., and see how they work and what they're good at. And I'll share some GitHub projects that you can use today in your projects. And of course, along the way, I'll share some resources as well. So let's get started. The first thing I want to get right from the start is the definition of those words, because they're used every day, everywhere, and a lot of time, well, I feel they're using correctly. So I want to make sure we're on the same page. So AI is a science. It's over 60 years old now. And the purpose of AI is to build systems that behave like humans, right? I would say probably better than humans, which would be an improvement. And so this means basically being able to work with human senses. So being able to see, computer vision is very important in AI, being able to speak, being able to understand speech, understanding the nuances of human language, the ability to reason beyond explicit programming, so basically learn behaviors from data, from rules, etc. And of course, the ability to predict, right? Which I believe is similar to intuition, right? Look at the real world, look at data, and try to come up with what's happening next. Within AI, there's a subdomain called machine learning, and it's probably one of the more popular and the more successful of those subdomains. And machine learning tries to let machines learn behavior and patterns from data. Okay, so instead of writing explicit code that would read data and do this with the data and then do something else, etc., right, which is the traditional way we write code, and we've been writing code for a long time now. Instead, we're going to use standard algorithms for classification, regression, clustering, and a lot of other things. And we're going to run those standard algorithms on data sets, okay? And by defining a number of variables called features, right? You could see this as the columns in your data set. We're going to build models that will let us predict, okay? But defining those variables, defining those features is actually a lot of work. And if you do machine learning today, you know that feature engineering, because that's how it's called, is pretty time intensive, right? So you extract data coming from a whole kind of different places. You run statistical analysis, correlation analysis, you visualize everything, and you try to come up with a set of variables, of features that looks nice. And that's what data scientists spend a lot of time doing, in addition to cleaning data, of course. So what about unstructured data? What about video? What about pictures? What about speech? What about unstructured text? How can you extract features from that manually? Is that possible? What are the features of my voice? What are the features of, if I took a picture of this room, what are the features here, right? What's important? What's not important? Is it possible to do this manually? So for a long time, some people tried to do this manually, and they got some results, but deep learning became very popular a few years ago, thanks to technical neural networks and other things like GPUs and cloud computing and etc. And deep learning is a subdomain of machine learning, and it's trying to do the same thing, right? Build models from data. But this time, features are extracted automatically, okay? So in some cases, there isn't any feature engineering at all. In some cases, you still do a bit, right? And you still do a bit of data pre-processing, etc. But most of the feature extraction actually happens automatically in the neural network, okay? And this is great when we want to work with complex data like videos and images, etc., etc. Okay, so that's what deep learning really is. It's a subset of machine learning that understands automatically the features in very complex unstructured data. And some people would want you to believe this is dark magic, right? Ooh, AI, ooh. Okay, and it's very, very complicated. So you should pay them a lot of money to do it for them, to do it for you, right? That's the age-old story of IT experts. Oh, this is super, super complicated, but trust us, we know. Give us money, we'll take care of it, right? And what they usually mean is, of course, they want your money, but on top of that, they want you to acknowledge that you're not as smart as they are, which I personally dislike very much. And again, the purpose of these talks today is to show you that everybody in this room can build and train and use deep learning applications, right? Literally. If you can read and write, I would say 50 lines of Python code, because a lot of it happens in Python, then you can do it, okay? So don't listen to this smoke and mirrors kind of thing. It's really bad. Because in fact, AI is three things. Sure, it's a bit of math, it's a bit of theory, especially if you want to build the new network architecture, you want to innovate in this field. Of course, you do need a very solid foundation in computer science and math and probabilities and a whole lot of things that I don't know about. But probably most of us want to use deep learning, right? We want to integrate deep learning into our apps. We want to build projects and products based on deep learning. So we're not trying to innovate on deep learning, we're trying to innovate with our projects. Okay, so if you look at the problem like that, then AI and machine learning are really a bit of code. And again, a lot of it is in Python, but you could use something else. And it's not a lot of code, as you will see, because we don't actually write the algos. We use standard algos, and we can use existing models. So we don't write a lot of code, okay? And of course, we need hardware. We need CPUs and GPUs to run the models and train them and predict at scale, okay? So code and chips, we know that stuff, okay? So let's start understanding what deep learning is. So I mentioned neural networks, so I should explain what a neuron is. So neuron is a simple mathematical construct. So it takes a number of inputs, okay, let's call them x1, x2, etc. To each input is associated a weight, okay, w1, w2, etc., etc. And all these things are, I would say, floating point values, right? So they're numbers. And the first thing that a neuron does when you show inputs to it is to take the inputs, multiply each input by the corresponding weight, and add everything together. And we call this multiply and accumulate, okay? So if you can multiply and add, you can do deep learning pretty much, okay? And so this gives us this activation value called U, or pre-activation value called U, okay? So let's pause here for a moment. We call this thing a neuron because we would like it to behave just like a biological neuron, okay? I have to say it's a very crude approximation of that, but okay. So how does a neuron work? A neuron, as far as we know, fires or doesn't fire. Okay, if a neuron is stimulated enough, it will send an electrical current. If it's not stimulated enough, it won't send anything. Okay, so we like to have this same behavior where below a certain threshold, nothing happens. Above a certain threshold, something happens. Okay, and that's a problem here because this function that you see here, it is a linear function, right? So if we change the parameters, if we change the weights, well, it's going to vary linearly, so we'll never get to see that threshold. So we need to introduce something else, and it's called an activation function. Okay, and the activation function is basically a simple math function that will introduce nonlinearity in the neuron. Okay, and over time, a number of functions have been used. The most popular one these days is that bottom one called ReLU. And as you can see, it's very simple. It's basically, so you take that U value and you take the max between 0 and U. That's pretty much what ReLU does. So if this value is negative, then ReLU will output 0. And if the value is positive, then ReLU will output the actual value. Okay, so that's very good because below a certain threshold, nothing happens. After a certain threshold, the neuron gets activated, right? The Y output for the neuron can actually be a very, very large value. There is no bound to that maximum value that the neuron could output. So if we have a very, very strong stimulation here, we could have a very, very large output here, okay? Which is what we want, okay? So that's what a neuron does: multiply, accumulate, and apply a simple math function to introduce a nonlinear behavior. Of course, one neuron by itself is not doing much, so we need to have multiple neurons. We need to define layers, and this is probably the simplest model you could build here. So it's got an input layer, okay, x1, x2, etc. It's got an output layer. Okay, we'll get to that. So we'll put the data samples here, and we'll read the outputs here. And in the middle, we can have at least one, and sometimes many more, hidden layers. Okay, and this is why this thing is called deep learning, because those models can be very, very deep. State-of-the-art models can have hundreds of layers, okay, hidden layers. So here we'll just have one, so it's pretty simple. So let's see what we could do with this. So of course, we need data. So we're going to define a training set, a data set, okay, a data set. We'll put this thing in a matrix called X, and I will put my samples on the lines here, okay? So X1, this is the first sample, X2 is the second sample, etc., okay? And as you can see, of course, I've got columns as well. So the lines are the samples, and the columns are the features. So for the sake of the discussion, let's say we're trying to classify pictures in categories, which tends to be an obsession for deep learning practitioners. And so these would be the pixel values, okay? The pixel values for the image, all right? So again, each line would be a sample, an image, and each actual value here would be a pixel value for this image. Okay, and I just stack them up like this, okay? And I've got M samples total, okay? Simple enough. I want to classify them, so I should train my model, and training the model most of the time means doing supervised learning, and supervised learning means you actually know what the result is, right? So you know that this X1 sample is category 2, and you know that this X2 sample is category 0, etc., etc. And you want your model to learn this thing, okay? So maybe category 2 is a cat, and maybe category 0 is a dog, and maybe category 4 is a lion, okay? And we're going to store these labels, as they're called, in a vector, and of course, I will have as many labels as I have samples, okay? And maybe in this example, let's say I've got 10 categories, okay? 10 different categories, and I'm using this as my N2 number, okay? So here, N2 is equal to 10, okay? So if we look at the model, we see, okay, we have L features, okay? So we should have L input neurons, input values here, okay? So each of those is going to receive one of those, okay? I'm going to take this sample, put it here. And I've got as many output neurons as I've got categories, okay? N2 again. So if I've got 10 categories, 10 different values here from 0 to 9, I need to have 10 output neurons, okay? That's how you build those models. But actually, it's not very practical to work with those category numbers. So what we're going to do is this. We're going to use one-hot encoding. And one-hot encoding is a simple thing, actually. It's a complex word, but it's a simple thing. So we're going to turn each of those labels into a bit vector, okay, with as many bits as I've got categories. So if I've got, let's say, 10 categories, I will have 10 bits here. And I will flip to 1 the bit that corresponds to this category number. Okay? So here, category 2, and remember we start counting at 0 because we're computer guys. Okay, 0, 1, 2, right? Okay, this is category 0, so I flip bit 0. This is category 4, so 0, 1, 2, 3, 4. Okay, it's called one-hot encoding. Why is this cool? Because now, actually, this tells me more things than this. This is just more expressive. Because I could see those as the probability that a sample belongs to a specific category. So here, I know that this sample has 0% chance of being category 0, 0% chance being category 1, 100% chance being category 2, etc., etc. Okay? I can see those values as probabilities. And that's very important because when I'm going to predict with my model, I will never get zeros and ones, right? Zeros and ones never exist in software. They do exist in chips, I guess, but software doesn't really know about zeros and ones, especially when you work with floating point values, right? So it's never going to be exactly 0 or exactly 1. It's going to be different values, and sometimes the network's not going to be very sure. So maybe, maybe it's going to be maybe 20% sure it's a cat, and maybe I'm 30% sure it's a dog. So, you need to have those probabilities, okay? So how does that work now? So I'm going to take a sample here, okay? Ideally, once my model has been trained, put that sample on the input layer, okay? Each of those features goes into one of the inputs. I'm going to run, multiply, and accumulate layer by layer, run the activation functions, okay? It's called forward propagation. And ideally, I should see this. I should see a 0 in the first neuron, a 0 in the second neuron, a 1 in the third neuron, because this tells me, hey, this is category 2. Okay, this is where I'm trying to get. Okay, if I get to that point, then my model is working fine. Okay, and the way I'm going to measure it is by running a whole lot of predictions and dividing the number of correct predictions by the number of predictions, and that gives me a metrical accuracy, which is probably the only thing I worry about when I'm trying to understand if these things work or not. Okay? So this is the purpose. Now, how do we get there? That's a different story. Because, of course, initially, all those weights corresponding to all those connections here, they have random values. Okay, we don't know what the weights are. So initially, when we predict, we get something completely wrong. Okay, and we're not even going to get a wrong category number. We'll get fully random values for each of the probabilities, right? So it doesn't work at all. And that's why we need to train the model. So initially, when we run that X1 sample through the function represented by the neural network, we don't get the right label. We don't get Y1. We get something different called Y prime 1. So in order to improve, we need to measure the difference. Okay, how close did we get to the actual value? So we need a loss function, which is a mathematical function which will measure the difference between Y1 and Y prime 1. Okay, and since those things are vectors, okay, it's more complicated than just subtracting Y1 and Y prime 1. Okay, we need to measure distance between vectors, etc. But all of the deep learning libraries out there provide those functions, so you don't have to write them. Okay, you can just reuse them. Okay, so we'll just compute the error. So in fact, what we want to do is we want to do this on a batch of samples, because we imagine we have millions of images we're trying to learn. Okay, if we needed to compute the error for each single picture and then adjust the weights, it would take forever. Okay, so we're going to do this batch by batch, and a typical batch size would be, I don't know, 32, 64, 128 samples, something like this. So what we're going to do is we're going to take one batch at a time, forward one sample at a time from that batch, compute the error for that sample, and then do it again for the next sample in the batch, etc. And we'll add up all the errors, and that gives us what we call the batch error. Okay, and it's also it's a way to speed up training, and it's a way to get to better training. Okay, to help your model generalize better. And then, once we've done this, we will adjust the weights in the magical fashion. Okay? So, the purpose of the training process is only one thing. It's to minimize error for that data set, okay, by gradually adjusting the weights. Okay, so we have, on each of those connections, we have a weight, okay, and we need, for each of them, to tweak that value, right? Remember, it's a floating point value. Tweak it up or down, right? Basically, we only have two choices here. So we need a way to do that. Okay? So why don't we just compute those weights? Because it's a function, right? We all know math. And we could say, well, okay, maybe I've got 25 or 30 weights here. Couldn't I just compute the optimal weights to have the minimal error? Well, the answer is no, right? Remember high school? You could do this maybe for 2 variables or 3 variables, or maybe a few more variables if you have a powerful machine. But remember what I said, those networks tend to be very large. They tend to have tens, maybe hundreds of layers, and that translates to maybe millions or tens of millions of parameters. And there's no way you can compute those values. You cannot compute the optimal weights. So you have to approximate those weights. Okay? And this is what the training process does. It's discovering iteratively what the right, I couldn't say right, what the hopefully optimal weights are. So this is how the training process goes. So you have a training set, you slice it in batches, like I said. You take one batch, push each of its samples through the model, forward propagation, compute the batch error, and then you run an algo called backpropagation, which will start from the output layer and will go back layer by layer. Okay, so this one first, these weights first, and then these weights then, etc. And just layer by layer, that's what I call backpropagation, all the way up to the input layer. And we're going layer by layer to adjust the weights in a direction that we know reduces error. And that's the magic part, okay? Because here, this output layer, this output value here, it depends on those 3 parameters. Okay, so for each of them, you could go up or down, right? So that's already 8 choices, right? 8 combinations, right? So you cannot figure this out just by chance. So you need a function that will tell you, an optimization function that will tell you, well, this one should go up, and this one should go down, and this one should go up again. And doing those 3 things will reduce error, okay? And we'll see how to do that. So you do this again, and again, and again, until you get to the end of the data set, and this is called an epoch. Okay, going through the data set once. And then you do it all over again. You train for multiple epochs. Okay, so again and again, you push those batches through the model, and each time you backpropagate and adjust the weights a little bit, all of the weights, layer by layer, a little bit, in the direction that you know reduces error. And so this is how gradually you get to very low error, right? Which means very good accuracy. Okay? And there are 3 parameters that are important here. So batch size is important. If batch size is equal to 1, training takes forever, and it creates different problems. If batch size is too large, then you don't get too many shots at backpropagation. So you don't learn very well. So you need to be not too large and not too small, which you'll hear me a lot saying today. That's the state of the art for deep learning. Hyperparameters shouldn't be too big and should be too small. Okay. The learning rate defines the step size that you take on those weights. So how large or how small are the adjustments that you make. Again, shouldn't be too large, shouldn't be too small. And number of epochs is how many times you will actually push the data set through the model. Okay, and these are called hyperparameters, and you have to get them right if you want the training to be successful. So how do you actually figure out where, in which direction you should adjust those weights? Let's take a smaller example. Imagine you have a function with two parameters, x and y, okay, and these would be weights, okay, in my previous example. And of course, depending on those weights, you get an output value called z, and let's say this is the error that I want to minimize, okay? And if I plot this function, it looks like this. So what I want to do is get to the smallest possible value of z by tweaking x and y, right? Okay. So I need to find that path. I could start anywhere. Remember, I start with random values, so I could start literally anywhere on that surface. And I want to get to the smallest possible value of z, which is that point here, right? The valley, so to speak, okay? And of course, you could solve this with 2 dimensions probably, but remember, we are really doing this with maybe 1 million dimensions, right? So if you can visualize this in 1 million dimensions in your head, welcome to planet Earth, right? I personally stop at 2, okay? Even 3 is impossible for me. So how do we get there? Well, you can read this very cool description. Okay, I'll just summarize it. Basically, we want to walk down the mountain, okay? But we don't know where to go. We're in the fog, right? Imagine we're in the fog. So the only thing we can see is we know we can take very small steps in some directions. So if you needed to do that, walk down the mountain, you would, okay, what humans would do is say, okay, yeah, this is up. Okay, this is down. Okay, so I know I could probably go that way. So I'll take a small step down. Okay, and it would start again. Say, this is flat. Okay. Oh, this is down. All right. Okay, I'm going to take a small step that way. Okay, that's exactly the way it works, except the algo doesn't feel the ground with its feet. Okay, it's going to compute partial derivatives for x and y. Okay, and that's the only ugly thing you hear me saying today. Well, I wish this was true. So it's one of those lies that Adrian warned you against. But okay, partial derivatives, remember high school derivatives, right? They give you the slope at any point on a curve or a surface. And once you know the slope, you know where is up and where is down. Okay, and I'll stop there because I don't want to hurt you. Okay, so this is what this function does. It will compute partial derivatives with respect to each weight for a given layer and then adjust the weight in the direction that takes you down. Okay? This is exactly what SGD is, which is the granddaddy of optimization function. This thing was invented in 1951, if you can believe that. And this is even 5 years before AI was actually invented. Okay, so it's a numerical optimization algorithm. You could apply it to many problems. It just turned out to be super efficient for deep learning. Okay, and the step size, okay, how you adjust, the adjustment that you make to the weights is actually based on how you define the learning rate, okay? So very small learning rate, you will make very small adjustments. A large learning rate, you will make very big adjustments, which creates all kinds of problems because if you make very tiny adjustments, it will take you forever to get to the valley, okay? If you make very big adjustments, you could be bouncing, you could say, imagine you have giant boots, right? Like in the fairy tales. You have giant boots and you need to walk down the mountain, but you can only take giant steps. So, you'll do something like this. It's going to look silly, and you will never get to the lowest point. Okay? So again, not too big, not too small. But do you think those things really look like this? Of course not. And this takes us to the fantastic and fascinating world of local minima and saddle points, right? And if you ever read Lovecraft's novel called Mountains of Madness, this is it, right? If you start reading about this, you will lose sleep and you will lose your sanity, and I'm living proof of that. Okay, so what's the problem here? The problem here is, of course, this function has very shallow minima, like this, for example, or this. And, well, this looks like a deeper one, right? So anywhere we start, we would like very much to end up here. Okay, but describing what I just explained, it's very possible I could start here and just, moving around, I would just end up here. And if I ended up in one of those local points, anywhere I would look would be up, right? Computing my partial derivatives, all the slopes would look positive to me, and like, no, there's nowhere else to go. I'm trapped here, so I'd stay here, okay? And this tends to give deep learning researchers a lot of bad dreams for some of them, okay? So that's a problem. Another problem, and here's another example, okay? This is from Andrew Ng's course on Coursera, which I recommend highly. He's one of the top deep learning researchers and one of the top educators. So thank you for letting letting me steal your slide, I guess. Okay, this is a really good one. Okay, so here's a good example here. And the intuition is that those things are not very, very likely, right? Because imagine they have 1 million dimensions. Okay, imagine your model has 1 million dimensions. To have a place like this, you would have to have a point in that space where all dimensions have the same slope. Okay, and the probability for this would be 1 divided by 2 to the power of 1 million, which tends to be a very tiny number. So intuitively, we could say, well, maybe they do exist theoretically, but in practice, they're very, very rare. But that's not a very satisfying mathematical proof, is it? So here's another problem that we could have. This is called the saddle point, and Andrew drew this, and he's a top deep learning researcher, but he sure cannot draw horses, right? This looks like a dinosaur. So it's a dinosaur saddle point, okay? You should publish it. So the problem here is, okay, visualize a horse saddle in your head and imagine that point at the top of the saddle, okay? So in this dimension, this point is a minimum, okay? So you remember high school? Minimum slope is equal to, how do you say that? Null, 0, right? Okay, so slope is 0, so fine, there's no slope, so I can't move anymore. In this dimension, right, the transversal direction here, this point is a maximum, okay? So the slope is 0 again. So if Mr. SGD gradually takes you to this exact spot, right, that's where you stay, because slope is 0 in all dimensions. So how could you decide where to go? Second nightmare for deep learning researchers. So somebody did the right thing and say, okay, guys, stop losing sleep over this. Let's take existing fully connected networks like the one I showed you and other networks, and let's look for those things. Let's try to see if we can actually find those points, right? In practice, so in theory, yes, they can exist. In practice, are they standing on the way between us and the minimum, and the global or the best minimum? So this gentleman is Jan Goodfellow, again, one of the top researchers in deep learning. And I'll let you read that paper. And in a nutshell, he says, well, yes, we can see them, but we don't actually fall into those local minima. Okay? SGD, for a number of complex reasons, is able to either go around them or escape them. But in practice, in the deep learning architectures that we use, this is not really a problem. Okay? Very, very, very interesting paper. Now, of course, practice. And in research, you always have I would say, the pragmatic guys who try to figure out, pragmatic solutions to real-life problems. And you have, people looking for truth, right? People looking for the mathematical truth of this. And of course, they can prove mathematically that there are plenty of those things in neural networks. So there's a lot of research still focusing on evading those, right? Building algos that will evade those points, okay? So you have those two schools of thought. The people who say, well, okay, it's not so much a problem in practice, and people say, yeah, it is a problem and we need to figure it out. So lots of papers on this. So here's another example of a saddle point. And again, that red ball here is vanilla SGD, and in theory, yes, it could stay trapped and not move. And over the years, a number of other optimization functions have been invented to kind of solve that problem, plus to bring faster convergence, right? And as you can see, some of those optimizers, they actually speed, right? They speed down the slope, because once they found the nice direction, then they can actually speed up. And that will mean larger updates to the weights, and that will mean faster training. Okay, and you'll see those a lot, the ADA something algos. ADA stands for adaptative, because the learning rate can actually change over time as you detect faster slopes or flatter areas. Okay. So if you want to read more about this, if you want to lose your sanity like I did, I wrote a couple of blog posts on this. And yeah, I'll take you into the dark corners of optimization functions and third-order saddle points. But right, be prepared. Right, open that door at your own risk. Okay, back to training. So we can train, right? We can train, and okay, let's not worry too much about those weird beasts. But what we want to know is how well does the network perform? So we're going to keep a small part of the data set, just like we do in traditional machine learning, and we're going to use it to validate, to measure the network accuracy periodically during training. Okay, and periodically in this case means at the end of each epoch. Okay, so at the end of each epoch, we'll take a batch from that, we'll take the validation data set and we'll just run it through the in-training network and measure accuracy. And hopefully this accuracy goes up, showing the network is learning. So this is what you should see if you plot all those numbers. So the training accuracy should go up, okay, pretty rapidly, and then it tends to plateau and stop making progress. If your network is large enough, if you have enough data, and if you train long enough, you will get to 100%, guaranteed, okay? It's called the universal approximation theorem. Try saying this fast 10 times. This theorem says, well, you will get to 100%, okay? And accordingly, the loss value will get to 0 or near 0, okay? And that's very good, because it means we're training correctly, we're learning that data correctly. But if you plot validation accuracy, you'll probably something like this. I'll probably see something like this. Again, increases very fast, plateaus, and then after a certain point, it drops and it doesn't recover, okay? And so you get to that top value here, which could, it's fair to say it could be earlier. It wouldn't have to be like top value and then down. It could be top value, go down a bit, plateau, and then drop, okay? Anyway, this is called overfitting. So overfitting is very bad. It's something you completely, you want to avoid. You want to look for this condition and you want to avoid it. Because what this really means is you train the network so well on the training set that it doesn't know anything else. And I give always the same example. Remember high school again. Remember your math exams. If you only practice on the examples that the teacher gave you during class, and you did this all over again and again and again, right? And you train your brain on solving them at light speed, right? Well then, come exam day, if you got one of those, fine. If you got something different, you couldn't do it. right? And that's the exact same problem here. If you train too hard on a specific set of data, then the only thing you can predict is that set of data and nothing else. Okay, so you don't want that, because what your users are going to send to your models, of course, are not training samples. It will be real-life samples. So you want your model to generalize to those samples, to samples the network has never seen before. Okay, not on the training samples. Okay, sorry. So you want the best epoch, right? Which is the one with the highest validation accuracy. So to make sure you don't miss it, because you never know for how long you're going to train, a good practice is to save the weights, right? After each epoch, during training, you save all the models at the end of each epoch. And then you plot that stuff, and you say, oh, okay, that's then epoch 132 is the best, and these are the weights I'm going to use, right? Okay, and if you have, like multiple peaks that are similar, you could even say, okay, let's compare 72 to 101 to 132 and run some validation testing again on those and see what happens there. Okay, so it's important to save those weights. Okay, so to sum things up, deep learning is, and I love this definition, it's about finding a minimum, not the minimum, right? That generalizes well, with bonus points for finding one fast and reliably. And why doesn't this say the minimum? Because first of all, let's go back a few slides. Okay, we could never be quite sure we found the minimum. It's actually an NP hard problem. Okay, so very, very hard. Solve it and you've got a few Nobel Prizes and Turing Awards waiting for you. So you'll never quite know where you are, in which minimum you ended up, but it doesn't really matter, right? Because if this minimum gives you an accuracy that is good enough to solve your problem, then is it really worth spending nights and weeks and months trying to find something else, right? So that's, again, the difference between, I would say, practical machine learning and, I would say, theoretical machine learning. If my business problem requires 95% accuracy and I get 95.1, I'm good, okay? I don't want to spend time chasing that 96 or 97 accuracy that maybe doesn't exist, right? And I will never know if it exists or not, okay? So you need to find a minimum. Okay? All right, that's it for theory. You can breathe now, okay? But trust me, you already know more than a lot of people who have machine learning in their job titles, right? Yeah. I do a lot of job interviews, and I could write a book about this now. Anyway, back to my topic. So now, what can we do with this? So we saw that fully connected model, right? The one that I showed you. And this one works very well for a lot of problems. But when it comes to images, which tend to be, again, a very popular use case, and we'll see this in the next session when we run demos, etc. We'll see that that fully connected network doesn't really perform very, very well for images. So a new architecture was invented in '98 by Yann Lequin, a French, very famous AI researcher, French guy. He's running the Facebook AI lab in Paris now. And he designed a network called Le Net, right? Good French name. Yeah, it's it's called Lequin, so it's good, right? Very good idea here. And this is what it looks like. And we'll run this one this afternoon, actually. So let me take you through the overview, and then we can zoom in. So we start from an image, right? And here we're trying to figure out it's a 60 kilometer per hour sign, of course. So we're going to run a mathematical operation called convolution. I'll explain that in a minute, okay, based on a number of filters. And these filters are going to extract features, okay? So they're going to highlight or detect certain features in the image. Okay, and throwing away a lot of information in the process. So since I threw a lot of information away, I can actually shrink those images. Okay, so this is called subsampling or pooling. And I can actually reduce the size of the image to keep the good stuff and throw away a lot of those pixels that mean really nothing. Okay, and I'm doing it another time. Okay, I'm doing it again. So I'm running filters again on those pictures, extracting more features, and then again shrinking or subsampling those images again to throw away useless stuff. And then I end up getting very tiny images, 5 by 5. I started at 32 by 32. And then I can flatten this 2D image into a vector, and I can classify it with a fully connected network, just like the one I showed you earlier. So that's the basic idea, that's the basic architecture you will see in CNNs. Steps of feature extraction, shrinking the image, doing it all over again, and then classifying. Okay? All right, new slides for Munich, right? You're lucky. Did those 15 minutes ago. Or no, more. 45 minutes ago. So convolution, and you know convolution if you've been playing with image manipulation application like Photoshop and so on, okay? Emboss, sharpen, blur, etc. These are convolution filters. So you take an image like this, and I have no idea what this animal actually is, right? I don't know, I'll figure it out for the next talk. And I apply this convolution operation, which really means I take this filter, which is 3 by 3, and I move it around the image, right? And you saw that on the previous slide, okay? That's the filter here. The dark blue thing moving, right, is the filter. So I slide this over the image, okay, applying the convolution operation, which is very simple. It's just you multiply the original pixel value by this, okay? You multiply the next pixel by this, and the next pixel by this, blah, blah, blah. You do this 9 times here, and you add the value, okay? And you just slide that thing, okay? And if you use this kernel, okay, synonymous for filter, the resulting image is this, okay? And you could say, well, this is probably, it's an edge detector filter, okay? So this filter, the resulting image is really the edge of that weird-looking animal, okay? And everything else, see all that's probably sand or whatever that is here, it's all gone. I don't need this. It's irrelevant, right? And if I knew what this animal was, then I could tell you it's a weird animal, okay? This would be enough to detect a dog or a cat or anything else, okay? And I threw away a lot of useless information, that background, the sky and the sand, and even the color of the eye just doesn't matter, and all the shades don't really matter. I mean, the outline would be enough to figure it out. Okay, that's what convolution does. And the purpose of training a convolutional neural network is to learn those values. Okay? So when we trained the fully connected network, we learned the weights on the different connections between the layers. When we train a convolution layer, we want to find what those values should be. So we start with random filters, and we train them again using SGD, the exact same thing, to discover what the right values would be in order to figure out this is what it is. Okay? And then pooling is much simpler. So pooling is shrinking the image. So in this case, okay, let's say these are pixel values. And I would use here max pooling, so with 2 by 2 filters. So I'm going to slice that image into 2 by 2 blocks, okay? And I'm just going to take the largest value here, okay? That's called max pooling. So here, I'm going to keep the 6, and here, in that green thing, I'm going to keep the 8, and the yellow, I'm going to keep the 3, and the blue, I'm going to keep the 4. And if you think about pixels, it makes sense, because this would be the brightest pixel. Okay, the black stuff, you don't want it, right? If you look at this, right? If imagine you're pulling on an area like this, okay? You want this edge. You want to keep the edge pixel, not the black stuff. Okay, so that's why max pooling makes sense. Okay, so what can you do with this thing? Plenty of very, very fascinating things. This is called object detection. So Adrian talked to you about recognition. Recognition does object classification. It tells you what you see in the picture, but it doesn't tell you this. It doesn't tell you where the object actually is and what we call the bounding box. Okay, we do this for people, but not for objects. And these are actually GitHub projects based on Apache MXNet, which I'll cover this afternoon. And these are MXNet implementations of state-of-the-art architectures like RCNN and YOLO, which it's really called that, but it means you only look once, which is a good name for a model like this. These are also called single-shot detectors, okay, because you take a single picture and you detect everything in there. Okay, so you can just go to GitHub and grab those and use them today. The model is defined, you have pre-trained versions, etc. One step further is object segmentation, which is finding the exact outline of people and objects. This is a state-of-the-art architecture called Mask RCNN, and this is as good as it gets, to be honest. It's very, very fancy. And this is, again, an MXNet implementation by one of our customers called TuSimple. And believe it or not, TuSimple do autonomous driving systems. So they tend to be pretty interested in where things are on the road, right? Here's another example. Again, this is another project based on MXNet for OCR, and pretty exotic OCR, as you can see, detecting letters with fancy fonts and curves, etc., right? And I mean, this one here is pretty impressive, I think. It's not my screenshot. It's really a very fuzzy thing. You could do face detection. So again, Adrian told you about recognition, but if you wanted to build your own version, you could do this. So you could find faces, and you could find attributes for all the faces. And it's fair to say they have a whole lot of attributes, right? I'm not sure if double chin is a very nice attribute, but okay. I don't see that one showing up in Amazon recognition anytime soon. So should you need this to solve your business problem, or chubby, right? If you want to detect chubby and double chin people, right? Don't run my picture in there, please. Well, there you go. You could use MXNet Face, again, which is based on MXNet. And this one is pretty fun. It's called Real PostTime Estimation, and it can do live pose estimation, so detecting the posture of the human body on the stream, on the video stream, in real time. And again, this is an MXNet implementation of that. Okay, and Facebook actually released a few weeks ago an updated version of this called Dance Pose, D-E-N-S-E Pose, not dance like dancing. And they can do the same thing, but they can actually have a wireframe over the whole body. So of course, once you can wireframe people, you can apply textures, and they have pretty impressive demos. So you should look that up, Dance Pose, but similar idea. So this is good, but pictures are just one thing, and it's not all there is. So what about predicting data, sequential data, right? You could predict 10 images in any order, and you would get always the same result, right? The order of those pictures doesn't matter. But what about, let's say, predicting Bitcoin prices, although that's pretty easy to predict. Or how about translating German to English or something like that? Or what about time series, right? What about predicting traffic jams in Munich, right? That kind of thing. Yeah, this happened. So here, sequences are important because for example, when you translate to German to English, of course, you don't translate word by word, right? The word that you use at position n depends on the word at position n-1, n-2, etc. Otherwise, well, probably I would just translate word by word. But okay, if you know what you're doing, you use context for each prediction. So you need those neurons to actually remember what they predicted a little while ago, okay? And so this is a new type of neuron called an LSTM neuron. And they can remember some past predictions. Don't worry, I'm not going to go and explain that one. Just remember that they keep some trace of the previous state. So they have memory, and that's why they have this very confusing name, long short-term memory. How could they be long and short at the same time? So they have short-term memory because they remember a few things about the past predictions. And they're long because you chain those neurons together to predict sequences. So if you wanted to translate 25 word sentences, you would need to have 25 cells chained one to another. Okay, so they are long networks with short-term memory, right? Better name for it. So very good for machine translation, for example. And a use case for this is actually an AWS project. It's an open source project called Sockeye. It was built by our machine learning team in Berlin. And it's an open source machine translation framework based on an LSTM architecture. Okay, and this is also used in Amazon Translate. Okay, this is one of the building blocks in Amazon Translate. Okay, so you can, in this case, this is an example of translating German to English. So you can just go and grab Sockeye and the data sets and train for a few hours or a few days and get very good results. Okay, but you don't have to design a model, it's already there. So if you need German to Russian, for example, which is not available in Amazon Translate, well, you could train your own model like this. Okay. All right. So as you can see, we can look at the real world. We can look at images, we can look at text, we can look at lots of stuff, learn from that, and try to predict and classify and do all kinds of very useful things. And deep learning is very successful, has lots of applications. But what about the other world, the one that we don't see? So, can you recognize those people? That's my test now. If you tell me who these are, you can win an AWS t-shirt. A nice one, come on. Don't be shy. Come on, you guys go to the movies, you know who these are. No? Sorry? So, they don't exist, right? Ah, sorry, you know, I'm a liar. Adrian warned you. Okay. These people do not exist, right? These faces have been generated. Okay, and it's not copy-paste, right? It's not the nose of Brad Pitt and the ears of Tom Cruise, and it's not like that. It's really looking at images from this celebrity data set. That's how it's called. This is an NVIDIA project. And learning how to generate people that look like the ones in the data set. Okay, so none of these are actually present in the data set. They're inspired by the data set, right? That's what I mean. You wouldn't find anyone in the data set looking like those, but you just learn how to generate people that are similar to the ones in the data set. Pretty crazy. So let's look at this one. Remember when you were 5 years old and you say, hey, daddy and mommy, I drew cars and trees and people, and this would be great, right? And this would probably end up on the fridge, right? I know my fridge is full of those. Well, PhD researchers they like to be 5-year-old too, but they call this a semantic map. Okay, so they draw this and they say, okay, this is the hood of a car, and these are just cars. And the red things are probably people on bicycles, and the green stuff is trees, etc., etc. Okay, and they take existing pictures and they label them like that. Okay, and then they train a model and they provide this as the input sample, and it generates this, right? And this is a generated picture again, and it's high resolution. You can zoom in, and you can see details. I'm not sure you can actually see the digits on the license plate, but you can see the rear view mirror. I mean, you can see some really fine-grained details here, okay? Just by providing something like this, right? And the model will literally fill in the blanks. This is called Semantic Maps. Okay, very cool architecture as well. But that's not it. And this, sorry, I forgot to mention, of course, these networks are called GANs, Generative Adversarial Networks. And they've been invented by Ian Goodfellow. Remember that guy? I mentioned him before? The guy who said, local minima, bah, right? Okay, he's a pretty smart guy. He's a pretty smart guy, right? Okay, and now GANs are getting crazier and crazier. So you could generate text from text. So if you wanted to write like Goethe or Shakespeare or Molière, well, you could do that, right? Ingest all of Shakespeare or all of Goethe and generate more text, right? You could generate text from images, so provide images and get captions, right? And the network would tell you, well, this is a red car and a tree, I don't know, something like that. And you could do the opposite, which I find pretty crazy, and this is this one here. So your input sample is one of those. It's a sentence, literally, right? This is the input sample. and the network will generate pictures, right? So if you say, this bird has a yellow belly, a gray back, and brown throat, well, guess what? You get a bird with a yellow belly and a gray back and a brown throat. Insane, right? This one messes me up, I have to say. You can generate audio from video. So you would train a data set with video files, including audio. And then you could give a video file without audio, like this train arriving, for example, or the fireworks. And the network generates the soundtrack for it. Right? And you can see for the train, for example, it starts very low, and then the volume increases as the train goes by. Or the fireworks, you can see, okay, very silent, and then bam, fireworks, and then silent again, and then bam. They have some, you'll find this one online. They have dogs barking, etc. So some of them are really good, some of them are just, But it's a start, right? I mean, this is a few months old, really. And the last one I want to point out is generating 3D faces from a single 2D picture, which felt like a challenge, because I think that's why we have two eyes, right? Because we need stereoscopic vision. But as it turns out, if you have a single picture, now you can build a 3D model of the face using deep learning, etc., etc., etc. I mean, not a week goes by without something happening on GANs. Okay, so it's going to make the unreal world even more interesting than the real world, I guess, until we can't tell the difference. All right, some resources if you wanna dive deeper on that stuff. So the top level page for machine learning at AWS, and this will give you an overview of pretty much everything Adrian talked about this morning. The AI blog, which is more technical, over there, with code samples, architectures, customer stories, etc. I mentioned MXNet quite a bit, so we will have a full session on MXNet this afternoon. But if you want to go and listen to the other talks, which is absolutely fine, because you can only take so much deep learning in one day, this is the MXNet website, and this one has an excellent technical introduction to deep learning and how to use it with MXNet. So it's almost like a deep learning book. Very good. If you want to dive deeper on optimization, gradient descent, and all those crazy things, on top of on my blog post, these are great. Sebastian Ruder is probably a German guy. Yeah, I'll run into him at some point, I guess. He wrote a couple of fascinating blog posts on gradient descent and all the cool techniques that were introduced last year to make this even more powerful. But this is math heavy and theory heavy, so you have been warned. And again, this is my blog with plenty of stuff on SageMaker, MXNet, etc., etc. And that's it for this first session. So thank you very much for listening. Please stick around for the chatbot session, right? Ian has a nice Lex demo, and I think he needs you to participate, so don't run away. And I'll see you hopefully after lunch for then a code level session on MXNet, running and training models, etc., and then a SageMaker session on doing that thing at scale and without managing any infrastructure. Okay? Thank you very much. Thank you.